All right, let's begin. Welcome back to the channel. Welcome back to the Magic Forge. I really appreciate you checking us out again, joining us on stream, checking us out on YouTube. If you like what we're doing, you want to see more, definitely like and subscribe. Hit that bell icon to be notified when we upload videos in the future. So to pick up where we left off in the last video, we were writing our test plan. We're still waiting on circuit boards to come in. So that's going to take a while. Probably not expecting until at least middle of this week, maybe not even until after Christmas, which is fine. We'll do what we got to do. I'll double check. We'll see what happens. But we won't be building a pilot board anytime soon, at least for the next stream. Let's see here. So it's Monday, so we should be able to have one more video or stream on Wednesday. Christmas Eve, Christmas. I'm not going to do any streams or videos. And maybe Saturday and the Sunday. Who knows? Maybe the boards will arrive then. So yesterday we left it off at our subsystem testing, step number 2, test number 2. The Hello World firmware on the ESP32. So I had, let's go here. So I had started opening this. Let's see if code freaks out. Okay. Let me, so what I had done was, come on, finish up. There we go, Mr. Code. So I had kind of started. For one thing, I just wanted to make sure I could flash and everything was working right. The IDF had an update. The extension had an update. So I updated the latest version, tested everything, make sure it would actually flash. Clean the build directory. So it was basically just a very simple. So we're going to build, flash, and then monitor. So we should succeed. I tested it before, but we're going to just double check now. So we should get the Hello World down here in the terminal, because it's just using the integrated USB serial interface used for programming. So we're going to go through the building steps. So I just want to kind of show you what we will be doing as we move forward. I'll probably be going into directories. All right, so it looks good. It's good. Bootloader. I'll be pulling some of my components out from my other builds to drag and drop, like the UART interface, the module, the header / C source file for it. That way we don't have to write it over again. So boom, it's resetting, and we have our Hello World. So this test, so I'm using an ESP32 dev kit. Some of this stuff we might not be able to write because based off of the pins that are being pulled out. So not all of these IO pins are available on a dev kit. Some of them go to like the integrated LED. I know at least one of them goes to the integrated LED that comes on the dev kit. At least the official dev kit. So you're not really able to use it. It's not really pulled out anywhere. But if we can gain access to these pins for the dev kit, we'll preempt and write our code. So this will be basically the first subsystem test that we're outlining here, the Hello World firmware. And we're going to say flash. The initial Hello World firmware can be programmed, so this test to make sure it's programmable. And it does give basic communication over the integrated UART port, which is perfectly fine. That's all that test is to establish. That's a basic subsystem test, and that's all we're looking for. So on the test log, that would be a pass. Now, I know we can set things up to where I can have all the hex files, all the actual files, the bootloaders and everything, you know, the partition and everything, and use the ESP32 programming flash tool. But I'm just going to do everything through VS Code, you know, basically upload it. I might be a little bit delayed also in pushing all this new source up to the GitHub for the project, for the project resources, because I got to make sure I update the git ignore in the main project directory. So ignores like the build and some of these files that you don't need to have. And I want to make sure like README and all that, everything kind of makes sense. Clean things up a little bit. Or just pull the READMEs out or whatever, or just update them. Because let's see, I think this one's just, yeah. So yeah, I created like a project Kickstarter for VS Code to make it easier, so I don't have to go through and create a blank project over and over and over again. I've just created it, a VS Code kickoff project that I just copy and paste into a new directory and clean up, you know, everything that I don't need and go from there. So then the README, I'll get cleaned up. We might as well. Hello world. That's firmware. Basic retail launcher. So again, these particular tests are basically for the first article test, the actual production level. Technically, everything should have been validated. You should have already proven that your design, your layout works. You can build a working board. So in actual production environments, it'd be a lot simpler. You wouldn't be jumping through all these hoops, and just want to reiterate on that. We got that. So open up the main. So that's all it does. So that would be that. And schematic, that would just basically test this guy. Test that and the USB UART interface to make sure that you can program. So now back to the ESP32. One of the other things, subsystems we need to test is the FTDI interface, or the basic UART interface. So let's go here. Now I'm going to kind of close this because that's already there. Now maybe we'll develop this firmware today, maybe not. SST. You know what? Let's kind of just copy this. And that way we get this flash the initial. Flash the. Let's get rid of that. UART FTDI firmware. Firmware and validate that the system can that basic communication, basic bidirectional. Information does happen over the UART FTDI interface. We're going to say J4. We're going to spell it out. J4. The computer flash the FTDI firmware. the USB to enter and to the PCB at J4 proper orientation. Putty. Okay, this, I need to worry about that right now. So we're going to need that. Let's not do that. Try to get rid of some of these unnecessary spaces to kind of clean it up. Okay. So we might actually have to develop some firmware. So let's go here. So we're going to name this URFTDI. Come on. Drag that off here so I can find what I'm looking for. Because I've got, driver libraries that I've been writing up. URFTDI, so what I need to do. Don't need build. Copy that. Yeah, because I want to, like I said, I want to. So this is kind of one of the things I do. Copy and paste, and that way I have a Kickstarter project. I have to go through all that. Your console. So that is the York console. Okay. So that one is, I think I definitely pushed that up to my original VS Code. I think it's there. I'll double check the license of the README. Not like it matters. It's stuff that you can already do. See here. Pull this over here because I need to reference how I've got it written. So we're going to open this up in code. All right. Ignore that. Let VS Code do its little thing first. All right. So we're here. Okay. Okay. Okay, so here we go. Copy this stuff up here. Hopefully it doesn't complain too much about that. So typically, so this would be called as a separate task. It would just be sitting there. That's why we're using RTOS. So delimiter, we're using a space as delimiter. So we need the RX pin. All right, RX. All right, so we need to RX. So we need to kind of reverse them. Well, we kind of already did. So IO 19. RX is 19. And then TX 21. If I have to reverse these in here, I have to reverse them. So we're going to go 115K. So what this will do, this will call the UART console C here. All right. Okay. So there should be enough here that we can do, because this is a generic console that you would have to edit to get to do anything you'd want it to do. So we also need to grab some jumpers. I need 3 to connect to my FTDI cable. Get that plugged in and kind of get this stuff going a little bit. Not as prepared as I should have been, and I apologize for that. Didn't know. Couldn't remember exactly where we left off and what we were doing. So I've got my UART cable here. So if we go to the schematic, so pin 1 is ground. It's going to be this guy. Okay, so it's orange and yellow on this guy. Ground. So let me grab my ESP32 a little closer, and I'm going to tie it in. So it's a ground. There's a ground. And 31 or 19 and 21. Are these pulled out? Well, there's 21. Might have to reverse these. I'm just throwing these guys in here, 19 and 21. All right. So, device manager, COM ports. So that should be USB, should be COM 3. Load. COM 3. Open. Okay, good. Why are you on COM 5? Nothing there on COM 5. What's on COM 5? No, I don't want COM 5. I want COM 3. Load. COM 3. Okay, so if I'm right, if everything goes according to plan, so what should happen is, so I'll knit that, and then it should spit this message out to Putty. But I haven't compiled this in a while, so I do not know. Let's build project. So we'll see what happens. So again, I might be delayed pushing all this to GitHub because I want to make sure I ignore like the build directories and the SDK stuff you don't need to have. I'll make sure all the README files are clean and relevant to what they go to. We could simplify what the... All right. Okay, you're mad. Okay. Are you kidding me? Are you kidding me? Oh. Maximum full path 250, so... Okay, so path. So it already failed up here. I don't know if it failed. Okay. include driver UART.h. UART console. Age. You know what? Console.age. What are you complaining about? Wait a minute. This is consumer console.h driver 22. Driver don't tell me. Now comes the really fun part of trying to figure out why these errors are happening. Sometimes something doesn't get resolved. And sometimes we clean it up and rebuild, it'll be fine. Let's try that. Yay, firmware development. This is why I don't do it for a living. I'd rather throw hardware together than go through this stuff. Okay, so it's probably mad because the path names are so crazy. Why are you upset about that? Why are you failing on UART.h? Let's see what happens if I try to throw it in your eye. Stop it. Include driver. Why are you... Okay. Why are you able to find it that way? And this is why I get mad doing this. UART.h. See if this makes any difference. I doubt it. Probably not. I hate this. Sometimes fighting VS Code is half the battle. The idea did update, so they might have put things in. So is there something in UART now? It knows that's where it is. No such file directory. Oh. Driver UART.h. You know what? I don't want to sit here and waste our entire time trying to debug VS Code and why it just doesn't want to work for this. When I compiled pretty much the same console for another application. It's not worth the effort and the frustration and the rage quitting. I don't want to do that. Let's focus on the primary thing at hand. Let's close that out. Let's not worry about that. I will fix that on my own time and figure out why it's not working. Let's just not. Okay. Okay, so we will have to suss this out, maybe kind of clean that up a little bit. So again, it's pretty much just going back to the spreadsheet and putting that in as an item. SST3 does the UART FTDI firmware and interface operate properly. Right now, I'd be no, but you know, we'll get this solved. We'll figure it out. And hopefully by the next video, I'll have this solved. So maybe tomorrow afternoon, I'll work on figuring that problem out. And we could suss that out. I don't know why it's complaining now about that driver. But then again, the IDF, the IDF did update. And sometimes they change things. I still have to go through the release notes and see if they did change the UART interface a little bit and adapt it for that new change. But we'll get there. But we're going to be sussing this out. All right. Four. Subsystem test 4. Now, if we go back, let's just concentrate on the important stuff, getting the test plan kind of written. So that test 3, test this subsystem. Now, since we're already here, D9 LED D9 verification. So let's give it a name. Status LD9 firmware. Now, and one each. About one. No, 1 second. Let's take Okay. So that's just a basic. It's going to be basic firmware. I could actually kind of probably write that since it's not a very fancy firmware test, but let's go ahead and close this. I don't need that right now. So go ahead and name the folder for it. Status sled 9. Maybe I'll suss out the firmware for it as well. Don't worry about that right now. So I don't want to sit here and fight VS Code the whole time. I just don't feel like it. I had to fight it for work at Sanksoft the one day just because all the changes and some things that VS Code had made, and oh my god, what a nightmare trying to do a Python script. Just getting VS Code to work sometimes and play nice is an adventure all in itself. It's almost like its own game. So yeah, you can make a video game based off of getting VS Code to actually play nice and work. So SST4, let me get these links copied down here. That way we have extras. SST4 does the red LED flash at the proper rate. Perfect. That's all we're doing. We're just making sure that LED was put on the board right, and the ESP32 does actually control it properly on that GPIO, on the proper GPIO pin. So that's, you know, multiple verifications that one, the LED is working and it is properly tied to that proper GPIO pin IO4. And the firmware will reflect it. So RS45 is going to be very similar to this guy. Because mind you, we're just going through the schematic sheets. No, we're not like putting to adapter to the PC and to the PCB at CN2. To observing proper connections A and B. So also, now I do want to note too that this is important to mention here. So if you look at the schematic, I do have a ground tie. Now, typically that would be used for like shielding in the cable. But one of the biggest things to avoid is having ground connected at both ends of a network like this. And that the biggest reason for that is to prevent a phenomenon called a ground loop, because ground is not ground at different locations. And no, it doesn't make sense. It's hard to it's a hard concept to grasp. But if you tie something to Earth, physical Earth, let's say at this location, and you have a device connected to physical Earth at another location, it's completely possible that the ground stakes that they're using aren't on the same bus. They could be different ground stakes at separate locations. Let's say if you're going across a plant. And because of that, Earth is Earth. It's the conductivity of Earth is going to vary from location to location based off of the mineral deposits in the ground. So you might actually have a slight voltage potential difference from point A to point B. And what that does is it creates a ground loop with that voltage difference. At best, ground loops don't really do anything, but they can inject signal noise into your lines. At worst, a bad ground loop can actually cause feedback in a system and put voltages where voltages are not necessarily desired, and could actually damage components. So typically in a system, you only tie one end to ground to prevent that phenomenon called a ground loop. I didn't explain it probably as well as I should have. It's a very interesting phenomenon that happens, and there is a lot more technically in depth. But as a general rule, you don't want to tie like the shielding of like a cable assembly, like the braided shielding, to ground of both ends of the connection. You want to try to avoid that to prevent the ground loop phenomenon. So that's why it's optional. I'm not saying to do that. In differential pairs, such as RS-45, RS-422, USB, CAN, Modbus, Profibus, anything that uses what's called a differential pair, you're not actually using ground. You're not actually kind of referencing ground. These two signals kind of reference each other in their own way. That is another science all in itself, how differential pairs work. But one is more is positive up to here, and the other one's negative down to here. That's the way that they meet and cancel each other out, is how the data is formed. And based off of that, they're extremely robust. There's a whole science behind differential pairs. And the way that they're designed to be the opposite voltage polarity is what gives them that robustness. They're really resilient to noise. I mean, you could have incredibly long runs of things like RS-45, like from, one side of your house to the other, and the devices will still be able to communicate. And especially if you have the proper termination and stuff to deal with reflections and other things like that. So it's a really cool thing. I definitely recommend actually looking up and reading into differential pairs and how they operate. But that understanding is it's really cool. That's why USB is such a high speed and capable protocol, because of the physical interface being differential pairs. And again, the same principle applies basically only to the cables, outside of the connector. But once you get to a PCB level of this, with your differential routing, you're not going to meet what's called coupling, which is the electric field, the electromagnetic fields between the differential pair wires. So there's a reason why in Ethernet they're twisted together, what's called twisted pairs. It's for the electromagnetic coupling that happens between them, which adds to the robustness and allows for more speed. It's a crazy phenomenon, more in depth than what this video series is going to cover, but it goes into more depth and understanding of why your cables are what matter more than what goes on in your PCB, especially for general low speed, low baud rate communications. Again, if you're looking at like high speed memory devices or MIPI cameras where you have close to gigahertz data transmission, gigabits, that differential routing actually matters on PCB. But for USB, even low end like RS-45, you're not going to do anything. It's just a drop in the bucket. You're just wasting time trying to get the routing perfectly, the differential pair routing perfectly. So I definitely recommend reading into it, looking more into it. It's really cool and a really good primer on understanding how this stuff works. So RS-45 test firmware. Again, we'll have to suss this out once we get the firmware sussed out. It'll be based on the UART FTDI firmware. But like I said, I remember that the ESP32 actually supports driving RS-45 chips. So it automatically can handle the direction pin. That way you don't have to worry about putting it in there. It'll automatically handle flow control. So we have to worry about that. That's no big deal. We got the test actually kind of sussed out. SST5. Let's put it on the log. 5 does the RS-485 interface function properly. And we'll devise, what we need to put in for like how to use putty. We'll suss all this out once I get the firmware actually working for the FTDI. We'll clean up the firmware and actually make a test out of it. So you just input a command and you get something back out of it. That's what we're just going to do. I was hoping to be able to suss it out, but VS Code wants to be a pain in my side, and I don't want to waste that time today. And we can at least suss this out, and we can get back to that once I figure out why it's giving that error on that driver. So we have that, RS-45. So that'll test this guy. Make sure we get communication in and out. Now we come to the limit switches. So we'll test. So the thoughts here is, how do we want to test the limit switches? How do we want to test them? Because there's like literally a multiple ways we can test this. So we can test them, these in the control switches. Obviously, I'm going to have separate tests, but do we want to have a separate test for each input, or have the whole block as a whole be one test? And you just switch over, click, 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 done. Because we want to test separate conditions. For one thing, we want to test using a different common here. So the whole idea of this, and let me explain the logic behind why I broke it out like this, why there's this jumper to connect this to ground or not. So let's say these are limit switches and you want to use micro switches. And it's basically a self-feeding system. So basically you'll be able to run 24 volts from your power supply through the input side of your switch, and the output side of your switch will come here to like input 1. But you'll have this jumper to ground, that way you're sharing the same ground plane. And that way when your switch goes, so your switch, you come off your 24 volts, I know you have to imagine, but your 24 volts, you come around, go through your switch, come here to input 1, it comes up through here, through the opto isolator, out through the common, and it'll reach here. With this jumper, then it'll go to ground. So that'll complete your circuit. All right. So that ties us to ground. So you can use it that way. Use the internal 24 volt, the same 24 volt power supply you're feeding this to do that. Now there's another way. The reason I did this is the other way, through something like a PLC. So a lot of PLCs will use like a drain output circuit, kind of similar to how I've it set up here with a transistor. It's kind of set up. So when your PLC says, "Hey, I want to activate this," it says, when it kicks an output, it's basically kicking an opto like this, basically doing the exact same thing. So the whole idea is you have this disconnected. The common, so it's called common, not negative or positive, it's called common, because then you would tie this to the positive power supply for your PLC system. So that would go there. And then your output from your PLC, let's see here, that would be Y would be an output. So X is input, Y is output. So Y, when your Y circuits would be connected to here. So then your 24 volts would come from here, from the common, all right, through here, and then through the PLC circuit, which would then take it to ground. So that way your 24 volts, actually your polarity gets reversed. So then your 24 volts is actually fed here, your positive comes up through here, up through here, up through the opto, and then out here, and it sits and waits until your PLC kicks on that output, and then it'll go through. So it's basically like an opto. So that's why I use AC/DC optos. So then you can have the type of circuit, or you can have your common be whatever. So common is technically not positive or ground, is whatever you want to set it to be. That's why I did it this way, so it can interface with PLC. So idealistically, we'll want to be able to test this under both conditions. So we're probably going to need some switches or a test button. So let's kind of go over to here. I know we have to keep scrolling up, but it's things that we need. All right, so tested Terry push button for limit so that's something we'll have to throw together. So I picked up some buttons and switches off of Amazon for doing some PLC testing on. So I've got a project box, like a panel box. I'm going to throw in. I'm going to make a cover plate for it and do some fancy, throw some lights on there, some indicator lights, some push buttons, and a couple switches to do some testing. Basically, like for PLC learning kit, basically for myself. And so I have plenty of extra parts. I can throw together a quick test button. So we will have to figure that out. So that's the real key here, is how do I want to test those? So it would probably be better off to have each input as its own test, and each method of testing it. It's going to get wordy and complicated, but you know what? We live for that. We live for that. Okay. System SST6. Okay. So the first thing we need to do so let's come up with a name. So that is limit testing. Again, control inputs and limit switches. We can technically test in the same with the same blocks. So we're just going to call this a generic term. But we're going to call this input test. I know, very, very, very descriptive, very, very original, but that's all we need. We're just going to test that. So we're going to use that, and we're going to test all 6 inputs. The biggest question is how we're going to do that. So we're going to flash the input test firmware. So we are going to test with the jumper. Install one jumper onto J2. We're going to test the internal interface first. J2 and one jumper onto J3. J3. This will connect the common circuits to the ground bus, called ground plane. Okay. So that's what we're going to do. So that's the first thing we need to do, is do that. So though this is breaking out what you have to do, it's only going to test one of the inputs. Okay, ground plane. So what we're going to do is we're probably develop like a series of flashes for the inputs. And we'll figure all that out. We'll suss all that out, but I want to kind of get the groundwork laid for this testing. Okay, so that's that. This will connect the common circuits to the internal ground plane. So connect the test button unit wire number 1. So I'm going to be to the 24 volt DC power supply positive connection. So yeah, I'm going to have the test buttons labeled. Their wires labeled. You should always do that. That way it's clear and concise. Connect the number 2 wire to, no, let's get here. We're going to do the first one. It's going to be limit switches, CN3, terminal 1. 3. Terminal 1. Okay. Check the status LED D9, I think is what it was. Well, I do have a test for that. Status LED D9 to see if it is flashing. If it is not, press and hold the test button and observe if D9 is flashing a single is indicating flash with a delay of 2 seconds. Okay, so because what we're going to do is like input 1 is going to be, 1 flash, input 2 is going to be 2 flashes, 3 flashes, then 4, 5, and 6. So that's what we're going to do to test all this. So, okay, if this test is not the number 2 wire, and the terminal from CN3. Okay, so boom. So we've got the first test there. Now what we're going to do is we're just going to copy this. Before I get too far ahead of myself, go to the spreadsheet. And SST6 does the input for CN3 won't operate properly. Oh, stop doing that. I spell right too. All right, save that. Okay. So before I get too far ahead of myself, connect the test button wire number 2. We haven't disconnected that, so we're just going to kind of connect the number 2 wire CN terminal number 2. Press and hold the test button and observe if DNA is a double flash with the delay with an interval of 1 second and a delay of 2 seconds. So a flash interval between flashes of 1 second and a total delay between the repeat of 2 seconds. Again, we'll have to write all this in. We'll have to write code. We'll definitely be sussing out more as we get the boards built, but I'm hoping to be able to do some test coding with this board again, so I figure out that that problem. Disconnect the number 2 wire from CN3. Okay, so here, those can be copy them. So just copy that, paste that, and be terminal 2. So then that's 7. Copy that. SST8. Connect number 2 wire to CN3 terminal 3. 3 is flash does not press hold this button. A triple flash. interval 1 second delay. This test is successful. Just number 2 wire from CN3. Perfect. All right. So we're going to copy this in the test log. Normal 3. So what this testing actually does for us, not only does it test these circuits here, but also validates that the common circuit is working right down here, at least to ground. So now we've got to go through and move on to the other inputs. Try to get this sussed out. Connect the number 2 wire to CN4. Yep, CN4 terminal 1. 4 terminal 1. And a quadruple. And CN4. That's another good thing about this. CN4 terminal 1. All right. Wordy, but the steps are simple. Again, these tests will be jumped through like pretty quick. Once you get into the rhythm, connect number 2 wire to CN terminal number 2 and a 5. I don't even know what the term for 5 pole. It's indicating a series of 5 flashes with an interval 1 second delay of 1 second and a delay of 5 flashes. Okay. P10. I don't want to do that. P. Terminal 2. All right. Now. Okay. Number 11. Number 2. Connect on number 12. Terminal number 3. Of 6. 3. All right. So what we should have now with this, what this should do is this should have, okay, fix my wording there. So those tests should have at least tested the common input. So the right thing to do would be to remove the jumpers and reverse polarity. So remove these jumpers and the hook 24 volts to terminal number 4. And then basically tie these to the negative of the power supply, simulating like how a PLC would be using. So that might be what we want to do. Who knows? I might see if I can devise a real quick test with the PLC and actually, have it run through testing on its own. They could just test each one of these and run through. We can actually test it with a PLC, which might be the actual move we should go. And that honestly, in some ways, sounds kind of fun. And would satisfy that requirement to make sure that, yes, I can trigger these inputs, I can control these inputs through a PLC. So, you know what? Maybe we can be a little adventurous, and I could see about throwing, doing a real quick program in the PLC to have one input and some time delays and trigger, kick off these outputs so we can tie them all together and just watch what happens with this board. That might actually be kind of cool and a good valid test. I mean, the easy thing would be just to put 24 volts here, pop these guys off, put 24 volts here, and test it the slow, boring way, but that doesn't test to validate that this can work with a PLC. And that's one of the key things I want to do with this, is actually test it with a PLC. So I think we'll go that route. And when we actually go to do this, you know, hopefully I'll have the webcam kind of set up a little bit better. I don't know. I'll do what I can to record everything, and you know, you can see the process and everything. So that gives me something else I need to work on. I need to get my well, I don't know if I get my training box built because I'm waiting on wire to come in. I've actually got properly color coded 18 gauge wire for wiring up my test box, my learning box. So when you deal with automation controls, there is kind of like a wiring color code system that you follow for that. Your white, your plain white, black, red, and green, or green with, you know, well, let's just stick with the black, plain white, and plain red. Those colors are typically reserved for your high voltage or your AC side. So like your mains coming in, be it no matter what phase it is, like, you know, single phase, double or triple phase. Those colors are usually reserved for that, for that side of things. So you don't mix it up with your DC side or your logic side. The logic side, so your positive in your logic is typically blue, solid blue. And then the DC negative side is typically either blue with white stripe or white with blue stripe. And I can't remember the wire I ordered. Let me see if I can see it here. Because I found, you know, don't mind me. I want to look because I can't remember. Oh, good, they shipped. It might, I don't know. I'm going to see if I can see the tracking number. So I ordered white with blue stripe. And those are colors reserved for, so blue, solid blue, and then like white with blue stripe or blue with white stripe are reserved to your DC circuits. Your low voltage side, your control side, and all that. So I've got the right wire coming in, and then solid green or green with yellow stripe. Those two colors. I prefer green with yellow stripe, but those two, you can use solid green. Those are only used for physical earth. Your PE connections, your earth ground. That's the only thing you're allowed to use those for. So I will put that out there. If you see somebody using solid green or green yellow, trying to connect something with actual voltage applied to it, smack their hands. That is against the wiring code, and you should never do that because you can put somebody's life in danger. Because that the green and the green with yellow stripe is reserved, I mean, specifically for physical earth, for safety and for grounding. So that is very important. So I would recommend anybody into this kind of stuff look into the standards and all that. So it says my wire is shipped. Let's see if I can find it when it's coming in. Oh, wait a minute. Shipped today. So let's see. I know you guys are hanging out with me while I look this stuff up, but I just want to see, because this is kind of relevant, because I'd like to be able to build this box. All right, so the label was created. It may not be here by the next stream, or enough time to for the next video, or to build up the box, but who knows? It depends where we are. I might be able to build it up before we even. Actually, I will be able to build it up before we go live, because there's, you know, with the board and stuff. So that's kind of cool. So yeah, we'll have to suss out the part of the test plan to cover connecting the PLC. We'll have to suss out the basically the firmware for it. PLC with testing program installed for testing program. So we're going to go and suss out the name for this testing program right now. We're going to call it P101 22 02501 test input. Let's see. I think I can give it a name, the click file. Let's see here. Minimum of 6 GPIO. Let's see. We can do minimum of 3 GPIO. 3 outputs on the PLC. I can't remember how many outputs, how many inputs or outputs I have, or this particular PLC has on it. I have to double check, but I think it's got 6 inputs and 6 outputs. If it is, that's more than enough. If it is 6, we'll definitely write the program and I'll clean this. We'll clean this up. But yeah, this will actually be kind of fun. I'm looking forward to actually doing this and setting this up and actually working with it, getting the Click PLC program working. So it's going to serve multiple functions for me. Furthering my knowledge on PLC programming and use and interface. And then also doing it for this project. So it's going to be pretty cool. All right, so we've got quite a bit here. There's a lot more to do. Still waiting on the boards to come in. You know, I've got you on the line. Let's just check. Let's just see. Might as well. We're here together, right? And I'm truly enjoying myself. Here. Look on my account. They've been shipped. Okay. So, okay, okay. So it looks like right now, so FedEx does have them. So it looks like FedEx has them. Looks like they were picked up today, earlier. Well, and it's from China, so the timing's different, but they're definitely on their way from China. So nice. This is really good. So they're on their way. So I don't really have. Let's see if I can. Trying to get the actual tracking number. Let's see if, because sometimes FedEx tracking, sometimes if I use the actual tracking number through FedEx, I can get a better date for delivery. Yeah, it's on the way. So it was 1 of 2 pieces. Okay. Yeah. Yeah, I have no estimated time, no ETA, so that's fine. That's fine. But they've been shipped. That's what's important. Cool beans. Makes me happy. It's good for this video series too. We'll be able to at least get those boards in and inspect them, and plan when we're actually going to start building the prototypes and the pilot board and start doing our testing. But I definitely want to get the test plan at least pretty much written, sussed out, get the firmware problem written, sussed out, figured out why I'm having issues with it, and go from there. Probably some changes in VS Code, but we'll go from there. So we'll call it. I thank you for hanging out with me and checking us out and sticking through this video series. I know it can be chaotic and hectic at times because that's the way life is. And that's unfortunately the way I am sometimes too. So I'll work on getting the gitignore file updated so I can push all the new stuff to GitHub. And you can have our current changes, but I don't know if I'll get that done today. I gotta suss out the gitignore file so it ignores all the junk I don't want to throw up there for you guys. So thank you. You have the rest of your nice rest of your evening, and I will catch you Wednesday. Awesome.